Hi, this is Dr. John Bergdorf again. In this video, we're going to explore what is meant by equal sets and subsets. Two sets are said to be equal if they have exactly the same elements in any order. So what's important is that the elements are the same, but the order of the elements is not. So for example, take a look at these sets, DOG, GOD, with no disrespect for either God or dogs. These two sets have exactly the same elements in them, a D, an O, and a G. The fact that they come in different order doesn't matter. These sets are indeed equal. We could even say, and use just very, very traditional notation, the set DOG is equal to the set GOD. So that's what it means for two sets to be equal. A set A is a subset of a set B if every element of A is also an element of B. So this is a related idea to equality, but different. Every element of A is also an element of B. This is the symbol we use to represent that A is a subset of B. Let's explore that with some examples here. So suppose the set A is the set 1, 2, 3, 4, 5, containing 1, 2, 3, 4, 5, and the set B is the set containing 1, 2, 3, 4, 5, 6, and 7. Identify the following statements as true or false. So the statement is, the first one we're going to examine is A is a subset of B. That would mean every element of A is also an element of B. Is it true that every element of A is also an element of B? Yep, they are all there. This is true. How about, is B a subset of A? So what we need to think about there is every element of B also an element of A? Here's a problem. 6 from set B is not an element of A, neither is 7. So it is not the case that every element of B is also an element of A. This is false. So that's very important to know that the order is going to make a huge difference. Now this next one may come out to be a little bit of a surprise to you. Is A a subset of A? So the reason this is probably going to be a surprise is when you hear the word subset. That sub prefix in there sort of implies that somehow the first set's going to be smaller than the second set. If you have A and A, well, they are equal. And so you might just jump in and say, okay, that's not true. However, the way the definition is written, if you state it in this case, is this. Is every element of A also an element of A? Is every element of A an element of A? Yes, it is. So a set is a subset of itself. And this one will probably surprise you even more. We're going to explore the idea, is the empty set a subset of B? Is every element of the empty set also an element of B? Okay, and that may make you think about that, but can you name an element of the empty set that's not in B? Can you name an element of the empty set that's not in B? Well, there's no elements to not name. So in fact, every element that there is in the empty set, and there aren't any, but every element of the empty set that there is an element of B. This, in fact, is true. And it actually leads to this very important observation that the empty set is a subset of every set. No matter what your set is, the empty set will be a subset of it. That's an interesting one. So we've talked about sets being equal. We've talked about one set being a subset of the other. We're now going to talk about what it means for A to be a proper subset of B. Now, subset and proper subset, as you might well guess, they're going to be very closely related. But let's see how they compare and contrast. Set A is a proper subset of set B if every element of A is also an element of B. So that's actually the same thing as the definition of subset, but there has to be one more criteria. And if A is not equal to B. Now this will be the word that will kind of fit what you might intuitively think. To be a proper subset, every element of A must be an element of B, but they can't be equal. So let's take a look at this. Oh, and here's the symbol for proper subset. You might notice it looks like the other symbol, except with the little, what looked like a little equal sign taken off, which implies they can't be equal. So if we have the set again, A, which is 1, 2, 3, 4, 5, is A subset of A? This is regular subset. Does that mean is every element of A also an element of A? That is true. But is A proper subset of A? That is false, because every element of A is also an element of A, but they are equal. So this is false. It's a subset of itself, but not a proper subset. Now, I want to just very quickly show you a little diagram that we're going to explore much more later in future videos. There's a device called a Venn diagram, which essentially creates a picture of set relations, where each set is represented as a circle. So in this Venn diagram, notice that the set A is completely contained within the set B. Every element of A is also an element of B, but A and B are not equal. That illustrates the idea of proper subset. A is a proper subset of B. We'll use Venn diagrams some more to look at set relations, but this is showing that A is a proper subset of B. Talking about subsets some more, and we're going to think about proper subsets too, let's do a couple of examples where we list all the subsets of a given set. Suppose your set has the elements dog and cat. So I'm not looking at the letters D, O, G as separate letters, as separate elements, but the element is a dog and a cat. So the subset is the set dog, cat. What are all the subsets? Well, one subset would be the set containing dog. Let me try to make that a little neater. That would be one subset. One subset would be the set cat. Those are definitely subsets. But the set is a subset of itself. So dog, cat is a subset of dog, cat. Notice I didn't say proper subset. And so you might say, okay, I think that's it. Looks like there are 3 subsets of the set dog, cat, but there's one more. Remember that the empty set is a subset of every set. So as it turns out, this is a good example of a set with 2 elements, and it will have 4 subsets. Suppose we throw in another animal, and you've got 3 sets. Looking at all possible subsets, well, we know that we could have the entire set, dog, cat, pig, so that would be 1. We know we'd have the empty set, because we've just talked about that, empty set, subset of everything. Let's see what else we'd have. Well, you could have just the dog, you could have just the cat, you could have just the pig. Those would all be subsets. But couldn't you also have the dog and the cat, or the dog and the pig, or the cat and the pig? All of those would be subsets, and let's see how many we've got if you count them all. We have 1, 2, 3, 4, 5, 6, 7, 8. The same thing would happen for any set with 3 elements. So a subset with 3 elements has 8 subsets. Now, of those 8, only 7 of them are proper subsets, because this guy right here would not be a proper subset, so I can't call that a proper subset. So 8 subsets and 7 of them are proper. Can you see a relationship in these numbers? It takes a little bit of effort to do so, but it turns out that what's really going on here is that 4 is 2 squared and 8 is 2 cubed. If you have 2 subsets, if you have 2 elements in your set, there's 2 to the 2 subsets. If you have 3 elements, it's 2 to the 3rd. So that gives you an important theorem that if a set has n elements, it will have 2 to the n subsets, that exponential relationship, and 1 fewer proper subset, since you can't count the set itself. And that is a famous and important theorem.